I'll write there one second. Okay, I'm here. Hi, everybody. What's on the agenda? Not on my fancy screen. Okay.
Can I ask a Princeton question?
Yeah, please.
From the exam, fall 2019. I mean, fall 2009.
Okay, fall 2009. That's an old one. Okay, fall 2009. Is it linked on our website somewhere?
No, but I could send it over Zoom.
Sure, if you have a link. Although, actually, I think I got it.
Yeah.
Which one? Exam.
Oh, final.
Okay. It's a deep cut.
Yeah.
Okay. Well, send the link because I actually don't have it. Sorry.
Sure.
Good. Let's see. Okay, I'm ready. Which one?
3B. I was wondering, yeah, like what's the procedure for finding that weight W that meets that criteria?
Okay, so for everybody's sake, let me summarize this problem. We got ourselves a graph. It's a weighted graph. We're trying to find a minimum spanning tree, it appears. The edge weights are distinct integers between 1 and 19. And there appear to be 19 such edges. Okay, so let's say we add an edge from D to I, which does not currently exist. And we want to know for which values of W is that edge in the minimum spanning tree. So I guess the first thing we need to know is the spanning tree. So let me copy and paste this thing into a paintbrush window, and we'll work there instead.
Cool.
Okay. So if we want to know the minimum spanning tree, we can use Kruskal's or Prem's. I guess the problem says use Kruskal, so I'll do that. So first we'll add, oh, well, maybe I want a different color. I'm using a mouse, sorry, so that's a little.
No, you're good. Thank you.
Clumsy. Okay, but all right, 1, 2, 3. Don't do 4. Why not? Somebody else other than the question asker. Why don't we include this one? Is my question too lame?
There aren't any cycles.
Or it is a cycle, right? Yeah. So if we include 4, it's a cycle. Okay, so don't do that one. 5, 6, 7, 8, 9 is a cycle. 10 cycle. 11 cycle. 12 not a cycle. 13 cycle. 14 not a cycle. Wait, yes, cycle. Everything's connected. 1, 2, 3, 4, 5, 6, 7, 8 vertices. Yeah, okay. All right. So then it says, imagine we add a new edge from D to I. So I will do it in purple here. New edge. And it has, well, I'm going to go all the way out here. Okay, and it has some weight. Okay, so the question is, for what values of this question mark is that an edge in the minimum spanning tree? So there's a couple ways to think about this. I mean, one is to just try some out. So let's say we pick 0. That's what I'm going to do first. So let's say we pick 0. Did you try that already out of curiosity?
No, I didn't. I had no idea how to approach this.
Got it. Okay, so let's say that was 0. well, now we have a cycle, right? Somewhere in the graph. Although the way I drew the edge makes it hard to see the cycle. So sorry, I'm going to redraw it. There we go. Okay, I'll put 0 here. So if we do 0 here, there is a cycle, right? Like we go all around this cycle. And so now we need to somehow make it a spanning tree. So what we can do is drop an edge, the one that is biggest in the cycle. And that comes from, there's a rule. I deleted some of the edge weights. I can't actually see them. What was this one again?
Which one?
Which one?
Oh, hold on. It's 7.
7, okay. All right, and this one's 2. Okay, this 5 was horrible. All right, sorry, one thing. Okay. So if we have this, and I said, okay, this is not a minimum spanning tree because it contains a cycle. Remove one edge, that's you get the minimum spanning tree. Is one way to think about what we could do here. So in this cycle, if I write all the edges in the cycle, we have 3, 1, 6, 8, and 0. So what we want to do is ditch this 8, like getting rid of that, and it would still be, then you'd have a minimum spanning tree. Does it make sense?
Yeah.
So this relates back to, there's a thing in the slides about the cut property. So this is a hard problem, but the cut property says that the way we prove the cut property, which was the underlying theoretical mechanism that allowed us to do Kruskal's and Prem's algorithm, it relied on this observation that if you ever had a cut where the minimum crossing edge was not in the minimum spanning tree, then there was a proof by contradiction where, okay, well now add the minimum crossing edge, that results in a cycle. You can then remove the other crossing edge that you had and you're left with this other minimum spanning tree. So like indirectly, what I just described, indirectly that is the inspiration for the technique I'm using here. It's kind of a deep thing, but let me describe the algorithm that I'm using here to construct a new minimum spanning tree. So it's add this new edge, di. Okay, this will result in a cycle. So do you agree with this fact that it results in a cycle?
I agree with that.
And it must, because we have more than v minus 1 edges. In fact, we have v. So remove largest edge in cycle. And so this is the hard part. So everything so far is like crisp. Then there's kind of a little bit of hand wave, and I'll say that resulting spanning tree. Actually, sorry. I'm going to go back just a little bit. All right, do you agree with me that if I do this, then we get a spanning tree?
Yeah, I do.
Okay. Now, the hand wavy part is, it is the minimum. It is the MST.
So we're saying the new edge is the minimum weight?
Or, sorry, we're saying the new edge. Well, the new edge doesn't necessarily have to be the minimum. Like whatever number I pick here, say I picked 5,000, right? I would add that edge, but that's the biggest edge in the cycle, so now it's gone. And so we're just left with the original spanning tree.
Oh, okay.
Yeah. So this is the hand wave in my argument that is, I think, hard given how we had a little less focus on the theoretical content of the course. Like it's in the Princeton students, it was just a little more focused on this. So I would say this is the really hard step, is to recognize that the spanning tree that you get back when you remove the largest edge in the cycle, that it is the minimum spanning tree.
Okay, I see. Yeah. And a question about that minimum edge.
Yeah.
Is that unique to the tree, or it pertains to a specific cut, like you assign each node a specific color?
Sorry, say that one more time. Just say it exactly.
Okay. So you know how we said that minimum edge connecting two vertices of different colors is guaranteed to be in the MST. Is that edge unique, or it depends on how we assign each color?
It
Like
it depends on how you assign the colors, yeah. And there's 2 to the v different colorings, right? Because for
Okay.
every vertex, you can either assign gray or white or whatever, red or blue. And so for all of those 2 to the v cuts, the smallest crossing edge will be on the minimum spanning tree, right?
Yeah. Okay. Cool.
Yeah. Now, in this case, I didn't actually think about the specific cuts. I don't think it's actually productive. I mean, you can think about this problem in that way, but I think that the cleaner way to think about this problem is just, well, when is DI going to be in, if we add a new edge, will that edge be in the spanning tree? So the way I thought about that is, okay, well, let's add it. And then to get the spanning tree, sorry, the minimum spanning tree, we'll remove the largest edge in the
Okay.
cycle once you add DI. So this brings me back to this question then. For what values of W, okay, this is my comprehension question for you. For what values of W is that edge going to be in the spanning tree? So for 0, will it be in the spanning tree?
Yeah.
Yes, right? Because we removed the 8. All right. What about other values? Or how big can it get until it, so that it stays in the MST?
It could go up to 8, but
Yep.
are we allowed to use duplicate weights or no?
So it's a little unclear. So what I would just say is for less than 8, it is in an MST. Oh, actually, so it's A. It says the word letter A. Okay, so less than 8 is yes. And then if we say 8, geez, I ran out of room. If we say 8 question mark, well, it is in an MST, right?
Yeah.
So,
Yeah.
So it's true that 8. So basically, I would say anywhere from -infinity to 8 is my answer.
Okay. And then what do you mean by like in an MST? Like, what does that nuance basically?
Well, so
entail?
a MST versus the MST. So if you have unique edge weights, then the MST is guaranteed to be unique. If you have duplicate edge weights, then you can have multiple different MSTs.
Okay.
Yeah. And so in that case, there would be 2 different MSTs. So if the value here is 8, there'd be 2 valid MSTs. It's just a matter of whether or not you use this purple edge or this red edge over here.
Oh, okay. I see.
Yeah, so that's why it's a minimum spanning tree.
Okay,
Yeah.
cool. Thank you.
Cool. All right. Anybody have a follow-up on this question?
Yeah, I do. That's why my hand's raised.
Yeah.
So I just wanted to clarify why it's less than 8. Is that because if we add anything like greater than 8, then it just doesn't make any sense because it's not the minimum spanning tree?
Well, yeah. So if
We
we add
would
9,
keep what
so
we
let's
had. Yeah.
do the X. So if we made it 9, right? Oh, oops. If we made this 9, then we'd follow this procedure. We would add this to the spanning tree, and then we would find a cycle, and then we remove the edge that is the largest in that cycle, which would be this edge. So it would not be part of the spanning tree. Does that make sense?
So you just get what you had beforehand.
Correct. Yeah.
Okay.
You end up right back where you were. Yeah.
Thank you.
Cool. Yeah. Other questions? All right. That was a fun one. I like that question. Cool. Spanning trees are definitely the weirdest topic in our class. Like if you talk to somebody who takes, like 226 at Stanford or whatever, like the CSC 12 at UC San Diego, they're unlikely to cover spanning trees. This is usually covered in a theory class, not a data structures class, but I really like it in data structures. And obviously Princeton does it. Yeah, Anthony. Oh no, you're in microphone that I can't hear mode again today.
Sorry, let me open.
Oh, there we go. That's good. Way better.
Yes, I just need to open my MacBook because I'm using
okay. That was the trouble.
monitor.
Got it. Okay, cool.
I just want to say, let's get back to the problem that we discussed on Monday on the spring 2019 final.
Okay, spring 19, problem 12.
I think it's number 7.
Number
the
7.
one with
Okay,
the quick meaning. I
Okay,
remember
one-
we were discussing that on Monday.
Okay, one sec. Let me open up this exam real quick. Oh yeah, so we're on problem 7. That's right. Okay, I remember talking to you about this now.
Yes.
Okay, am I sharing the right screen? Yes. All right.
Yes, that's right. my data structure, I was thinking about using a hash map, using a hash
Okay.
map.
A
The
hash
type-
map from what to what?
Yes, it has key, integer, and value integer.
Sorry, one sec. Let me, yeah, even with your laptop open, the sound is just a little crappy, but
Yeah, I'll just bring myself closer to the
it's
microphone. So
a little better. Yeah, but it's interesting. It's still not quite right, but that's okay. We'll make it work. Okay, so you're planning on using a
hash map with key, integer, and value integer.
okay, got it. All right,
Okay.
cool. And so it tells you what? Like, what does the key represent?
The key would represent the actual value that we're going to insert.
Mm-hmm.
The value will represent the parents.
Uh-huh. The pairings? Oh, parents. Value
Parents,
is the parent.
P-A-R-E-N-T,
Key
yes.
is the item, value is the parent. Okay, so that seems probably reasonable. So then when we add something, what do we do? I'm gonna call your map M.
Yes, so we say
M.put,
n.put, and I'll put P, the variable P for the for the key, and for now I would set the value to null.
Okay, got it. So there's no parent. All right.
Yes.
Sounds good. Oh, I guess I should give this thing a variable name up here, and I'm not going to bother with the constructor. I am going to do it for new, so that you have a new hash map. Blah blah blah. Okay.
Yes.
All right. I know how vertex exist should work. Vertices. Vertices is supposed to be a list of all the vertices. That's not that interesting, but let's do connect. Okay, so what does connect do? Actually, sorry, we have to do root first, because to understand how this uses roots, let's do root.
So roots. I was thinking about calling the root function recursively. So I would get, so I would put the base case something like if the value is not null, if the value is null, then return P. If not, then I will put the value in the argument and call the root function recursively.
Got it. Okay. Otherwise, return root of m dot get p.
Yes.
Yeah. Okay, that seems reasonable. So you climb up the tree. M dot get p null and return p. So if something is not is okay, great. All right. So then what? How does connect work?
Yeah, I think that's it for the root function.
I think so. Yeah, it's close at least. I think it's a good idea. Sure. And then what about connect?
Or connect, it doesn't matter which one is the key or the value. So
got it. So you're saying like m dot
like
put
n dot put and
p-root,
whichever p root and q roots.
Got it. Okay. So this answer is probably right. If it's not right, it's wrong in some very minor way. So I think that the
yes, and I have the solution for this one. It's already posted on Ed.
Okay, good, cool. But yeah, I mean, I think that this way of thinking seems great. So it's a good choice of data structure. It allows you to seamlessly move, around. Let me see if I can spot any issues. I mean, the basic idea is totally solid. There just might be some corner case. So if the map gets P and that's null, you return P. So you're your own parent. I'm just a little worried that you can end up P. I think it's fine. Yeah, okay. Sounds good. The null, like these are an alternate solution where instead of putting null, you do p, so that a thing is its own parent.
I see.
But I think this is fine. Yeah. I just had a slight feeling of alertness around the fact that there was a null getting, stored as a value somewhere. But I think it's okay. Yeah. But if there is a bug, it's related to that. I don't think there's a bug, but if there is a bug, it's that. Seems good. Great.
I see.
Cool. How do you know it works? In real life, well, you'd write some tests, and then you'd find out in a hurry if you had any bugs. Alrighty, what's next?
Hi, Professor. I have a question. Not necessarily related to content, but ecal questions. Can I save it for the end?
Sure. Well, no one's asking anything, so go now.
Okay. I was actually talking to Alex about this earlier, and I was kind of looking forward for to spring or to fall 2021 about kind of bringing a decal for either of the core CS 61 courses, specifically geared towards reentry students, kind of like a parallel as like a helper. But my question is, I kind of don't know how to reach out to a professor or like what kind of questions to ask. So
yeah, I mean, it's not, sponsoring a decal is pretty lightweight. They want us to only sponsor one a semester. You can do more if you are already full up. I think I'm actually doing 2 soon. But let's see. So who would be the right person? I mean, I would say I would target. Well, one person you might want to talk to is Michael Ball. I think his title will let him sponsor a decal. So I'd start there. He seems like a very natural fit. So check with Michael Ball, and feel free to reach back out to me if that doesn't work, but that's who I'd start with. The other type of person I would reach out to is anybody who joined the faculty pretty recently, because they're like, less likely to be running a decal already. Because it's pretty lightweight, honestly, to help run a decal, right? Like we just have to, like the more work you do for the person that's trying to do the decal, the better. But yeah, like, I've helped. I've been the sponsor for a 3D printing decal, for a number of semesters, and I basically show up and like go to the end of semester project party. But other than that, my role is pretty minimal.
Thanks.
So basically, it's a light ask. But Michael Ball, that's who you start with.
Perfect. Thank you.
Is dynamic programming in scope for the final? We didn't teach it this semester, so nope, you're good. It was in previous semesters, and you probably spotted it on old exams, but yeah, it's just not a topic this time around. Which isn't always clear, of course, right? Because it could always be buried in some lecture and you didn't notice it, so. All right.
I have a question if no one is willing.
Yeah, go for it.
It's a little bit personal in terms of project 3. So we spent 3 days with this, and I'm just really curious how the comparison between the world that is generated with interact with input string and I guess it's doing that actually through running the actual world, but it's basically comparing something that's been quit and loaded with interact with input string. And for the life of us, we couldn't do it. And I suspect that it's because of our lighting system, because in our lighting system, we were actually serving up a different world to Terra render that we would modify for the lighting too. This was something we did for, I think, Ambition or Gold.
I mean, I believe I'm not mistaken, the way that the algorithm works is it just calls interact with input string and then takes the, I'll just pull up the grader code real quick and double check, but I think it just calls interact with input string a couple of times and then compares the output, or maybe many times. I think grader is relatively simple. Let me look. Nope, wrong thing.
Yeah, this took 3 days to troubleshoot. We still don't figure it out.
Oh no. Well, let's see. Which test were you failing? Test same input string with movement leads to the same tile array?
CO1.
CO1. Okay, got it. Oh, that's the one with save and loads. Okay.
Mm-hmm. And we were passing this before we implemented lighting, but we weren't passing any of the other stuff.
Yeah. Okay. Let's see. I'm going to extract the key lines of this thing. So annoyingly, it's probably something really small and uninteresting. I think that's what I've learned about all bugs. They're never interesting, or very rarely interesting.
This was fun programming with someone this closely. We actually peer programmed the whole thing, so we're always on a Zoom call.
Ooh,
so this was an
cool.
illuminating experience. But God, was this troublesome in terms of Git? No, like that's 70% of our time was like Git.
Yeah, I mean that's the world, I guess. It's sort of funny because it was probably a very small decision you made that ate 2 days ago.
Mm-hmm. Totally, and we knew this, so we were just kind of going sequentially over it and tried so much. We actually read up on debugging online, both of us, to see.
Good experience.
Good for this.
Totally. All right, let's see. Almost there. So.
Ooh, one more question. Could it be because we were actually saving a save outside of like it was in project 3 rather than in core or somewhere there?
Hard to say. Let's see. One moment. I'm just going to show you the structure of the test, and we'll see if it matches your intuition. Let's see. Engine. All right. This is essentially. Oops. Okay, here we go. This is the rough structure of the grader. I got rid of the stuff that wasn't that interesting. All right, here we go. Engine. So basically, it does the following 20 times. It creates a new engine. It calls interact with input string on an input and gets back the tiles you return. And then we create a TE tile character grid of those. This is a class that we have that does equals comparisons. And we'll come back to that in a second. Then it iterates over a split version of the input. And by split version, we mean that it's going to, like, an example of this input would be, you know, So that's an example of input, and then a split input would be just the same thing where there's some like Q, it's :Q, right?
Mm-hmm.
And then I guess
the next one is L and the continuation.
Yeah.
Hmm.
Got it. Okay, so it looks like that. So then it creates an engine, a new one, mind you. Then it calls interact with input string, and then it just reiterates. So every time it's creating a new engine, because there should be no state stored in the engine variable itself. It all has to be wherever you're storing your text file, right? And so then once it's done, it then just does a W1 equals W2. And then I guess the other interesting thing is what a TE tile grid is. So T tile car grid. Where is this defined? All right, another question.
Okay, that's odd.
Okay, so then this is the equals method for a TE tile car grid. So what it requires, we do arrays.deep equals, which means that every single, like, let's say W1 6 must be true. So if you have some lighting thing where the two tiles aren't considered equal, right? Like you have two different, this is using the TE tile, right? So that, if you're doing something where the tiles are no longer considered equals after loading, it's like, I don't know, maybe the lighting is slightly different than, I don't remember what the TE tile equals method looks like, but yeah. So this is the test that you're basically facing.
But both are through interact with input strings.
Yeah.
But it's not like comparing to like a stock staff representation to our our implementation.
No, it's just literally yours. Yeah.
Okay, this is going to be bothering me.
This is just. Can we run it through your interact with input string just as a whole thing versus a split version of same?
Oh, this is awful. I thought maybe it was like an issue with the way we interact with the test now, but we messed up somewhere. That's not gratifying.
Yeah. Well, this hopefully is helpful for tracking down whatever weirdness is going on. Yeah.
Oh, yeah. Well, this was fun.
Good. CS course covering dynamic programming. Someone asked which ones. CS 170 will talk about that sort of topic in great depth, actually. So if we look at like what we've been doing very recently has that feeling. Let's see, let me share this. So if you want to know, 170 is probably the class at Berkeley that's most like 61B. Like the programming angle is not so much, but the theory side, it's very close. Like this, it's the same kind of thing in the sense that, but it's more kind of philosophical, right? So they talk about divide and conquer as a first class topic. We did divide and conquer, like merge sort and so forth. We just didn't call it such. But then they also do like depth first search and shortest paths again. But then they actually step back and start talking about things like greedy algorithms. So some of the class algorithms we talked about in class are greedy algorithms and some are not. We had dynamic, so then there's dynamic programming as a flavor. And we actually also kind of did this. I mean, in 61A, when you do Fibonacci and you memoize the answers to the smaller subproblems, that is dynamic programming effectively. So this is basically, in the same way that merge sort is an example of divide and conquer, memoization in the context of Fibonacci numbers is an example of dynamic programming. So this is the philosophy of dynamic programming. Then you get into some weirder stuff that is, we've touched on some of this, like network flow is another kind of even weirder graph problem than minimum spanning trees. Linear programming, I can't explain it quickly right now. And then later there's this sort of what we were doing more recently, like this idea of reducing problems to another, or in our bonus extra lecture lately, like NP completeness. And then they go even weirder into, I guess, quantum factoring that semester. But I bet the last few weeks vary a lot. So I think 170 is like just a really cool and beautiful class. Yeah. There's no lecture in regular expressions in this class, in 170. If you wanted to cover regular expressions, there's basically two different places that regular expressions come up. One of them is practical use. Like I want to use them to do something. That happens in, I'd say, I've done it in 61B before. Maybe I'll put it back sometime. I know it definitely exists in Data 100. It kind of can pop up in all kinds of places as a practical tool, but I would say Data 100 is probably the most likely place that one will encounter it these days. there's a second place that regular expressions come at, which is in the theory of computation, because they turn out to have really, like, there's a deep relationship between things like stacks and regular expressions and Turing machines and other things like that. So I think the class that might talk about this is CS172. Regular languages. So CS172 will cover regular expressions from the perspective of theory. But from practical perspective, I'd say data 100 is the most likely place. But basic regular expressions, you can pick it up pretty quickly. I have also taught it in this class. So if you just want to see me do it, I don't think I did it in this semester. Spring 18 probably has it. So if you just want like the purely practical, I've really not taught it that long. Okay, 17. Yeah, there we go. So if you just want to know the basics of regular expressions and want me to explain them, by Josh at, yeah, otherwise, see data 100. For theory of regex, see CS172, successor to CS172. Okay, my world generator. So let's look up the spec. It's actually pretty cool. Like this was my third algorithm I came up with. And I think mine is the most mathy and like the simplest, most mathy approach. So it works a little bit like this. I think I might have mentioned this in the previous Q&A, but I did actually. But basically it has a starting room. So it generates a room with a random XY and a random width and height. And then it plops it down in the world. And then for each of the 4 walls, it, with some chance, creates a new room. And so what that does is then it, in this starting room, it only had the up direction. So it puts a hallway. Then it creates a new room, in this case, just to the top left of that. And it creates a room that was a box. And then from there, let's see. Then it basically said, okay, I can't go back down because I just came from there. There's some chance I go left. In this case, it did go left. Some chance I go right. In this case, it did go right. And there's some chance that I go up. I'm not quite sure. Oh, this is down. Oh, it did do down. Okay, so this is a room that created a left, a right, a down, and an up room. This down room happened to be width 1 or size 1, so it's just a, it looks like a hallway. This one had width 3 and height 2. So basically, it's just like a recursive thing that spiders out. And if it ever goes past the edge of the world, it just doesn't make that room. Now, one side effect of the way I did this is you'll notice all the hallways in between rooms are 2 dots long. And that's just because it was easier to program that way. And the aesthetics were fine. And that was my whole story. Yeah, so just recursively does it that way. And then by construction, everything's connected. There's no gaps in the floors, all that kind of stuff. Yeah. I don't know if it's the most aesthetically appealing, but it's not bad. And it felt good to write. What if it doesn't go to an entire side? Yeah, so you're right. There's a chance that maybe a big chunk of the world never gets used. The way I get around that is that the probabilities are low enough that by construction, it just happens to fill the space most of the time. And it's kind of like the percolation problem, right? Like in the percolation example, on the percolation assignment, if the probability that a cell is open is at least 60%, then you always percolate. And same deal here, right? Like my probabilities are just such that you tend to fill the space. You can create special cases though, like if you only fill less than 20% of the room, then restart. But yeah, seems to work out pretty well. Yeah. Now this, what's the how do? Decide which to branch. Just in every room, you decide left, right, up, down. You'd like check each of them. You iterate through each of the directions and you say, I don't remember what it was, like a 20% chance or something that you'll happen to go in given directions. So you try to go all directions. It's just that only some of them get picked. And if, for example, you go right here and you plop down this huge room, when you finish the recursive call on the right side and you come back to the down direction, let's say you pick a down direction, but the room overlaps this, then you just don't make that room. Yeah. And yes, it does appear that there are some rooms that are 1 by 1. So there's these funny features like this. This is a 1 by 4 or 4 by 1, however you want to call it. Yeah. Yeah, so I think this is nice, but I don't think it's quite as beautiful as perhaps other approaches. If you look actually someone posted on Ed a pretty interesting, like someone building dungeons based game, and someone stepped through the whole process. Apparently it's a somewhat common resource for people to use for this project, where someone just walks through their whole thinking process. There's other things you can do though. You can do like the full-on Dwarf Fortress approach. This is like world generating base game Dwarf Fortress, where they like set out a space, like a world, and then they like simulate rain and rivers and erosion and whatever else. And you know, you can do all kinds of crazy stuff. Yeah. There is no way to play each other's games without sharing your code. However, in the spring of next year, I may try to make it so this project can work. But right now you have to share your code. Now, one thing is, we plan on allowing people to just freely share their code online completely. So yeah, if you want people to use your game, you just post on GitHub. I haven't put that out there yet, but yeah. Starting this semester, we're gonna let people just post their code. And then next semester, we're gonna have if we can make it work, I hope to have a client server model where whenever you write your game, you will provide both a client and a server. And so people will be able to just provide the client. And then what I'd like to do is actually allow multiplayer. But yeah, so you are allowed, but this will be a thing we're going to put out as a post. So right now it is currently not permitted according to the rules of the website, but we're going to put out a post saying it is now permitted. So yeah.
Just for this project?
Just for this project, yes. Not the others, because I'd like to avoid full-on plagiarism. Because the other projects, it's like everyone's doing the exact same thing. So sharing code, I think, leads to bad outcomes. But sharing something where everybody's doing something slightly different, I think, can be okay. Yeah. Yeah. All right, what else do you guys want to know? Any hands up? Let's see. Yeah, Sufi, what's up?
Yeah, I had a general question about MSTs and SPTs. So I know that like sometimes when you get a minimum spanning tree, like it could potentially be a shortest path tree for like a specific source. And I was wondering if there's like a good way of going about finding if it is.
Ooh, that's a fun question. I like that a lot.
Because I just do trial and error, you know, and I was wondering if there's like a better way of doing that.
So the trial and error approach. Tell me your trial and error approach.
Honestly, it's just picking random sources and just running Dijkstra's on it and then seeing what happens.
Yeah. Oh man, I gotta say, your entire framing of that question was perfect. Thank you. I'm proud to hear you ask that question even. Like, anyway. Yeah, good. Because I feel like I've infected your mind with the right way of thinking about things. I'm pleased by that. Anyway, so what would be a better way than just running Dijkstra's from every single shortest path tree? That's a very interesting question. So the runtime for that, Dijkstra's is basically E log V, right? The runtime. Does that sound right to you?
Yeah.
Yeah, I think it's like E plus V times log V, but E log V is simpler. So E log V for Dijkstra. So if you do that for every vertex, it's VE log V. So the question is there a faster algorithm than VE log V to tell whether the minimum spanning tree for a graph is a shortest path tree for some source? I don't know. That's a really beautiful question.
Because there's also like the case where like it's just not at all, right?
Yeah,
you could have a graph where it just doesn't even.
Yep. Yeah. I don't know. That's a really good question. I suspect the answer is, I bet there is a faster algorithm. I can't really see what it is off the top of my head, but, and you're right, it does have to also give an answer, which is no, right? Like the result could be any vertex number or it could be none. That's cool.
Yeah, I'm gonna definitely look into that because I've like found myself like having to go through every single. I mean, sometimes you can look at it and kind of tell if one is just not gonna work, but I'm thinking about every single one essentially. So
yeah, that's cool. I don't know. That's a great A+ level question. That's beautiful. What I hope is that there's some nice reduction, like create a family of new graphs that you run one Dijkstra's on once or something. I don't know what, but fascinating.
Yeah, I'm sure there's something out there, so I'll look into it for sure.
Yeah. Why would you have to call Dijkstra at every vertex? Well, you don't. It's not necessary that you have to. It's just that I know that algorithm will work. Because basically, what the algorithm is going to output is a set of vertex numbers. So basically, we want to create an algorithm that takes a graph G and an MST on that graph. Let's call that M. And verifies whether that the MST, oh, sorry, and how about this? Gives a list of vertices for which the SPT for the is the MST. I think my grammar might be slightly screwed up there, but yeah. So one way to do this is just run Dijkstra's from every vertex. And if it matches the MST exactly, well, then include that one in the list. So I think there's probably a faster way than doing that, but I don't know what it is. All right, Ryan. Did you have a question or you had a hand? Okay, cool. All right, Anton, what's up? Oh, I see. Where can I find these live lectures though? Oh, so a lot of them are posted in the guides. I'm lazy about reposting them because really the viewership is like very low. So it's been a bottom priority to get them up, but I will, because I know that those who are here might want to go back and look and see something I said. The question was just asked about what do we use as the source for the MST? So the MST doesn't have a source. If you use prims, there is a source that you use just to find the MST. But in general, there is no, when you talk about an MST, there is no such notion as an MST in general. All right, Anton, then Phoebe, then I got to go.
So Alex said something in discussion that kind of intrigued me, and it was I couldn't completely understand it. So it's about everything being breadth first search, everything being a Dijkstra, and kind of continuing up into sort of more theoretical computer science. Dijkstra becomes the foundation, and kind of everything prims. Everything is essentially BFS, or can be thought of as Dijkstra. I wonder if
got it. And so this is in the context of graph problems, is that right?
Yeah.
Sure. Yeah. So there is sort of a unified graph traversal algorithm that basically consists of start with some vertices on a fringe, and then pop vertices off that fringe and add new vertices as necessary. And a lot of graph algorithms can be viewed that way, right? Like if you want to find the shortest path, it's just a matter of who goes on the fringe and in what priority order, right? And what you do when you visit a vertex, that kind of thing. So let's say you want to find like paths through a graph where the vertices have numbers in them, and you want to find all paths whose like vertex or all cycles where like the sum of the vertices in that cycle are prime or something like that. Even weird problems like that, you can boil down into some kind of graph traversal where you're just pulling things off a fringe and then performing actions at vertices. Yeah. So in 188, you go into that in a little more detail. Not as fully though. It's kind of a 170 topic, kind of a 188 topic, but yeah. But it is cool.
Thank you. Yep.
There is a Hillfinger project, if you're curious. I'm sure
Enigma?
there's a version of this, but so we go to, oh wait, sorry, it's not. So we go to 61B, fall 14. So the last project, if you want to do this sometime, it's kind of a cool exercise. It is a weird one. I find this a strange way of thinking about programming, but this project, let's see, to explore how graphs algorithms are all quite similar. See, but I think that everything should be accessible, and I have a getting started video here. And the slides for this project are here. My first semester at Berkeley was funny, by the way, where I was co-teaching with Paul Hillfinger, and I feel like my job was just to make the projects digestible by humans. But yeah, so this is a pretty interesting project to explore that topic further. Or the beginning of 188 also does so. Okay, Phoebe, I'm gonna give you the last word today. I am gonna do this again next week, Monday, Wednesday, Friday. So this is not the last one. Friday, I plan to do a live lecture so that I can, have everybody feel like there's a sense of community again. Yeah, so Monday, Wednesday, Friday next week, I'll be doing this again. But Phoebe, what do you got for me as our last word of today, at least?
I just had a couple questions about P versus NP.
Sure.
And I guess if if people are still trying to solve it, because from what I could tell, it looked like the implications of having it solved could be kind of negative for society. And I was wondering if that's being addressed.
Yeah, I mean, it's interesting because, it would be positive and negative. The negatives you're saying would be like e-commerce is broken. You might put some mathematicians out of a job. I mean, I don't know.
Break like security on a lot of websites.
Yeah, the security on websites is a problem. I mean, I think there are workarounds for that. If you're willing to have slower encryption, there's actually this thing called Russell Impagliazzo's 5 Worlds. Hold on, I find this thing. It's a really cool paper name. Yeah, here we go. Like, you got to check this out. Okay. That's at least one blog post about it. Let's see. So there's actually, there's a lot of open questions about this. It's not just P equals NP, but there's other things about like whether or not cryptography can actually work. So there are, so Russell Impagliazzo, he's this like really interesting math dude at San Diego. Very, very, he's definitely like your typical like eccentric math genius. I remember when I met him when I was interviewing at San Diego a long time ago, that like his office is just like, I remember being messy like some professors are, but he's the only guy I know with like tons of crumbs all over the floor. So not to hate on Russell, of course, but he's definitely a guy, he's a man of the mind, let me say that. And he's thought very deeply about a lot of things. And he's kind of like not quite in our world is the way I think about him. So anyway, that said, he has this really interesting viewpoint that, there's a lot of different questions about what's possible. So if we look at, actually, I'm gonna go back to this blog post. Like one world we might live in is one he calls algorithmica. So in the world, if we live in algorithmica, we don't know. But if the nature of mathematics is such that P equals NP, then it is the case that, we have all these cool things we can do, right? We can solve all these problems. Yeah, that could be a good or bad thing. There's like, and on the other end, we have cryptomania, which is, the thing we do right now, public key cryptography, where I can send messages over open channels. That's something I could do on the internet today. So maybe it's the case that we live in cryptomania, maybe not. But if it's possible to factor large integers, we know we don't live here. So if anybody ever finds an algorithm that can factorize large integers into their component primes, then we do not live in cryptomania. So it's basically like a whole set of 5 different worlds that he has in mind, which are kind of interesting. So certainly people have thought about this problem a lot. Like if someone manages to solve P equals NP, like things break. Actually in a way, quantum computation is kind of a baby version of this, where it's coming down the pipe. And when it gets here, the pipe, whatever, is it pike, down the pike? Down the pike. Sorry. Pike. So it's down the pike originally, yes, but people say pipe. Anyway, beside the point. So people have thought about how quantum computing is going to break everything. And so, there are moves to start switching encryption over well in advance of any quantum breakthrough to keep ourselves from running into trouble. Yeah, so that's one question. You had another one?
That was all. Thanks.
Okay, cool. Sorry, that was more answer than you bargained for. Okay, I'm going to run so I can be ready for 195, which is happening immediately. But I'll try and get these Q&As up soon. I'll see you guys next Monday. All right, see ya.
Do we have a Q&A section on Friday?
Trying to leave. My Zoom let me leave. My controls. Oh, there we go. All right, cool. Bye.